All right, let me start the recording. Okay, so we're going to be looking initially at homework 3, problem 3, before getting into lecture 7 in the notes starting chapter 5 of Felder and Roussel. So the homework problem is going over a juice production, making juice from concentrate. And so we're looking at a facility that's taking in 60,000 pounds per day of cranberries, which contain 69% juice by mass. And so these berries are fed to a machine, which mashes and extracts the juice. And after those mashers, it's sent to filters, which separates the juice from the insoluble cranberry material, the like stems, the outer skins, the pulp, things like that. And so what's done there is then the juice is fed to an evaporator, which removes a significant amount of water from the juice. And then you have a concentrated juice product. However, some of the juice is bypassed around the evaporator in order to produce a pleasing product. It happens a lot in the food and beverage industry where some processes, while removing things that we don't want in our product, may end up in a off-tasting product. And so the simplest way to address it is to mix it back with some of the original material to recover your taste, while at the same time keeping the undesired, whether it be water or a contaminant like a mineral or something like that, from your product. So the final fresh juice is noting that it contains 98% solids, dissolved solids, with the stream from the evaporator containing 68% dissolved solids, and the final product containing only 30% dissolved solids. And so this problem is a little tricky. It's a little hard to grasp. And so I think it's a really good candidate for us to kind of take a look as a class and see what we can come up with together. All right, so the first step, as always, is to draw a flow chart for this process. And so what we have is a process with 3 major unit operations. We have our masher, our filter, and our evaporator. Hold on 1 minute. I'll be right back. Give me 10 seconds. Hold on. All right. All right, so we have our 3 processes, and we have to identify our major inputs and outputs, keeping in mind we also have that bypass. So we had, what did we have coming in? We had 60,000 pounds per day of cranberries. And our masher allows us to separate our undissolved solids from our dissolved solids. So this is our bulk solids. You know, we can call it our pulp, whatever you'd like. Then we have our juice, the juice bypass. And the evaporator, which removes water from our system. And then finally, with that, we have our concentrate. And our final juice product. All right, so now we can start filling in with the information given in the problem statement. So the system states that the fresh juice product contains 9 weight% dissolved solids. So I'm going to say for this 9 weight% dissolved solids, I'm just going to label it DS. Labeling from the concentrate, we have 60 weight% dissolved solids. And the final juice product has 30 weight% dissolved solids. And that means it's essentially, if we're quantifying juice as water and dissolved solids, the balance should be water. So if this is the concentrate, for example, is 68 weight% dissolved solids, then we have 40 weight% water. And if the final juice product has 30 weight% dissolved solids, then we should have 70 weight% water. And here we have 91 weight% water. Everyone following so far? All right, one last thing we can mention is that our feed contains the 69.6% juice, which is our water and dissolved solids. That means we have approximately 30.1% pulp, or the insoluble material. So if we have our masher and our filter working properly, such that all of that pulp is being removed, then we should have 30.1 weight% of the 60,000 pounds per day coming out here in our filter. I should say 60,000 pounds per day. Here, I'll put it down here actually to make it a little more organized. So we can do a balance here over this filter. So if I do a balance on the filter, then I should have leaving in this stream here 60,000 pounds per day times 0.301, which should be about 18,240 pounds per day. Cool. And I can put that in my process in terms of calculated value. So I'll make it green. That means if I do a balance on the filter in terms of a juice, what's leaving the filter as juice should be that 60,000 pounds per day times 0.696. I can erase it. Actually, this should be should be 0.4. It's not going to change my number any. So I have 60,000 pounds per day times 69.6, or 41,760 pounds per day of juice. So I can fill that in here. What was it, 40 something, 41,760. Right. Everyone following along with that? Okay. So this is the part where it gets a little tricky, right? Because I can look at a balance here at the split, here it recombines, as well as over the evaporator itself. So where do you think we should look at next? Where would you guys want to look at next?
The water stream from the evaporator.
All right, so we can look at the water stream from the evaporator. So this is where it gets a little tricky, definitely. I'm gonna zoom in a little bit. So if we have water stream from the evaporator, or just it's really a water balance on the evaporator, I should say, more accurate. So I know going in, I have 91 weight percent, and here I'm gonna make, let's do some labeling of streams. This is here. I like being colorful. This is M1. This is M2. This is M3. M4, M5, M6, M7, and it's important to do this kind of as you go to stay organized, right? So I've got 9 streams, and we're going to be looking at a balance involving streams 5, 7, and 8 for right now. So I have 0.91, because it's 91 weight percent water, times the flow rate of M5, which is my input, which is equals my output, because I don't have any generation, consumption's a steady state, there's no reactions. So this equals M7, because it's pure water, plus 0.4 times M5. 8. So currently, I have 3 unknowns, right? I don't know any of the flow rates. I know the breakdowns, but I don't know the actual amounts. So I'm going to kind of just make a note here that I've got 3 unknowns. So I'm going to underline them in red, saying, okay, I got to figure this out. 3 unknowns. So let's look at another balance. Well, I can do the same thing on the evaporator if I'd like for the juice, but it's going to be dependent on this. So it's not going to help me a whole time. But what I can, and I'll write it out just for completeness sake. So juice balance, shouldn't say from evaporator, on the evaporator. So I have 9% of M5 equals 60% of M8. And there's nothing leaving the evaporator, right? So I still have my 2 unknowns. But let's take a look at a couple other things. Maybe looking at a balance here where M8, 6, and 9 come together. Actually, we can circumvent this a lot more. So let me do this type of balance, right? I'm going to look at an overall balance, right, of my process. So which streams shown here leave my process?
Water and products.
Water and products, but also my bulk solids, right? So M3, M7, and M9 are my outputs, correct? And I only have one input, which is M1. So let's look at a particular balance and you'll see why it will really help us. If I do a dissolved solids balance, overall balance on the process, which streams over my process involve my dissolved solids?
M3, M6, M8, M9.
Over my process.
M3, M9.
It's only going to be M1 and M9 because the dissolved solids, not looking at the pulp, the dissolved solids go from M1 to M2 to M4. They split into M5 and 6, then they go into M8, which they recombine to M9. So my dissolved solids go into my process at M1, and they only leave my process at M9. So if I look at a dissolved solids overall balance, I have M1, and 69.6% of that stream is my juice. And of that juice, 0.9 weight percent is dissolved solids. So this is juice and feed, and this is dissolved solids and juice. that has to equal M9 times that final concentration of dissolved solids, or 30 weight percent. Does everyone see that? Or I should, to be more consistent, 0.03. And M1's known, it's 60,000 pounds per day. So if that's 60,000 pounds per day, what does that make M9? It should be about 12,528 pounds per day for M9. So now, with that in mind, I know the amount of final juice product I have. And if I know my input M1, as well as the outputs M3 and M9, I can then find the amount of water leaving in M7 due to an overall balance. Which says, if I look at an overall global balance, M1 has to equal M3 plus M7 plus M9. M1 is 60,000 pounds per day. M3 was 18,240 pounds per day. And M9 we just found at 12,528 pounds per day. So what does that make M7? Well, that should make M7 about 29,232 pounds per day. So now I can go back to my diagram and put that in. So is everyone following along okay? So thus far, I'm able to determine 1, 2, 3, 4, 7, and 9. The flow rates that we do not have are M5, M6, and M8. So going back to my process here, I now have M7, but I don't have M5 or M8. So I still have two unknowns here. But I also have two unknowns here. So with this, I have two equations and two unknowns. Because like I said, I know that M7 is equal to 29,232 pounds per day. So if I solve the evaporator's water and juice balance simultaneously, I should find, write that down, via two equations, two unknowns. I should get that M5 is approximately, let's see, go to my notes. Let me do this calculation. $34,468 pounds per day. And my concentrate should be about 5,159. So now with those, I can then solve for M6, which should be 41,760 minus M5, which was 34,000. I'll write that out. M6 equals M4 minus M5, which was 41,760 pounds per day minus 34,468 pounds per day, which should equal let's see, what does that equal? About 7,369 pounds per day. Might be some rounding issues, but there's M6. So now we have all of the streams identified. The tricky part, definitely for this problem, was understanding the importance of the overall balance in solving this. Because knowing that the dissolved solids only leaves the process in one stream, it allows you to find M9, which then you can use to find M7, and then finally solve the evaporator via a balance on the unit operation itself. If you try to do it beforehand, there'll be too many unknowns to solve. So going back to the problem statement, it asks, after you draw and label the flow chart, at what rate is concentrate being produced? So that would just be the flow rate of M8. So concentrate produced. Let me scroll back up. Where's M8? No, this isn't M7. This is M8. 5,159 pounds per day. The next thing that's asked is what fraction of the juice by mass bypasses the evaporator. So the fraction of juice that bypasses the evaporator that is simply M6 over M4, which is 7,369 pounds per day over the total 41,760 pounds per day, which is 0.176. Going back to the problem statement, it says how many kilograms of final 30% solids concentrate is made up per kilogram of berries fed to the process. That's essentially how it's asked. It sounds like you would really need to do the unit conversion, but you would find if you converted both the final product and the berries coming into kilograms, the conversion would cancel itself out. So the easiest way to answer this is do a ratio of M9 over M1. So M9 is that final juice product, which, going back to my process, 12,528. Pounds per day over 60,000 pounds per day. And just to kind of show you that the unit conversion doesn't matter, 2.2 pounds is 1 kilogram here at the top and also down here at the bottom. So that essentially multiplying by unity changes it from pounds per day to kilograms per day. So it's really just 12,528 divided by 60,000, or 0.209 kilograms product per kilogram berries. So 20%, 20.9% is your final, quote unquote yield. And the last question it asks, it says the reason some of the juice bypasses the evaporator is to preserve volatile components, which add to the flavor and aroma of the juice. Identify a change through the process which would allow more of the volatile components to make it to the final product. What are some drawbacks to that plan? Well, for part E, the easiest thing you can do is to manipulate the bypass evaporator operation, where you put less in the evaporator and you just get a more higher and higher concentrate of product that you mix back in. But you can run into issues with the evaporator not working properly, because as you pull the water out, those dissolved solids will most likely no longer be dissolved, and you can run into some issues. So are there any questions on that homework problem? No? All right, so then let's start looking. Oh, did somebody say something? Or was somebody working on a blender? All right, so let's start looking at getting into chapter 5, looking at single phase systems. Where in this, the primary focus is understanding the implications of the ideal gas equation and non-ideal equations of state. So a couple of things before we start talking about the ideal gas equation are the concepts of fluid compressibility. Well, a fluid is considered incompressible if changes in pressure do not cause significant changes in density. This is likely going to hold for liquids, solids. Items that are compressible are going to have significant changes in pressure, or in density, excuse me. As a function of pressure. And these are going to be vapors and gases. So it's important to understand this implication for density as we consider, or at least begin to consider, equations of state and how species react to changes in both pressure and temperature. One of the things that's we like to assume is this idea of volume additivity. And this is for ideal mixtures where you have similar molecular structures among species in the mixture. a good example is you can have a mixture of hydrocarbons, polar systems. So long as the molecules are structured and behave similar, volume additivity is more likely going to be hold. And what we mean by volume additivity is if I have, 2 mils of A, I'm going to add it to 3 mils of B, I can assume that I have 5 mils A and B. Versus a non-ideal system, you can have drastically different things. So this would be ideal. And then non-ideal, if you had 2 mils A, 3 mils B, you might have some interactions. And so that volume additivity doesn't hold. And so we can define and describe volume additivity as the density of a mixture, or the mean density, is equal to the sum of the density of each species times the mole fraction, the mass fraction of each species. And you can also define it in terms of specific volume, which is 1 over the density, and say the specific volume is equal to the sum of the specific volume of each species times the mass fraction of each species. So let's take a quick look at an example. So if I wanted to estimate the density of a 50% aqueous solution of sulfuric acid, knowing that the density of sulfuric acid is about 1.834 grams per cubic centimeter, and that of water is 0.998 grams per cubic centimeter. If I assume volume additivity holds, or is valid, I can calculate the density of the mixture as the density of the sulfuric acid, 1.834 grams per cubic centimeter times its mass fraction of 0.5, plus the density of water, 0.998 grams per cubic centimeter times its mole fraction, mass fraction of 0.5. Doing this calculation, I get a density of 1.42 grams per cubic centimeter. And if I wanted to test or check my assumption, I can look up the density of that mixture in a reference book. The most common one that we use is Perry's Chemical Engineering Handbook. And so if we look up from Perry's, we can find that the density of this mixture as reported is about 1.3951 grams per cubic centimeter. And so the error in my assumption doing this calculation would be 1.42 minus 1.3951 divided by 1.3951, which I get about 1.5% error, which in the grand scheme of things is fairly low. So for this system, I would say that assumption is valid. So is there any questions on that brief discussion talking about volume additivity and how you can find densities of mixtures based off mass fractions?
Do you care which formula we use? Does that matter?
That's a really good question. In theory, it really shouldn't matter, but in practice, you'll often find that doing the calculation both ways, you'll get slightly different numbers. For example, if we looked at doing this last example, finding the density using specific volume, you'll find that the density that you calculate in the other method is about 1.29 grams per cubic centimeter, which is drastically different than the 1.42 we just calculated. And so, is one better than another? It's really hard to say. My rule of thumb, what I typically use is the one that we kind of shown in this example, and this one here. I would say that this one's a little more accurate than the specific volume calculation.
All righty, thank you.
Of course. All right, so let's start talking about ideal gas and equations of state. Which I call EOS. An equation of state is a relation that describes a species, volume, temperature, pressure, and amount, i.e. moles, together based off assumptions on how the molecular species behaves. And I know that's really vague. Primarily because an equation of state is simply a function that lumps these values together in a meaningful way such that knowing certain properties of a species allows the calculation of the remaining. And so, and which equation state is necessary largely determines on the nature of the molecule itself. Meaning, certain equations of state work better for hydrocarbons than for polar substances. And whether we can describe a molecule or the state of a molecule as ideal or non-ideal is often dependent on the values that we want to calculate altogether. Simply put, we can assume something's ideal, but unless we know all the properties of that species, it's hard to be confident in understanding whether that assumption is valid. And so we're going to talk about today is ideal gases, because when we're talking about these kind of equations of state, we're going to be really focusing on gas equations of state. Liquids we can talk about, but that's mainly for multi-component systems. Gets a little tricky. We'll touch base on that in chapter 6, but what we're really going to focus on is looking at gas systems and the influence between what is constitutes an ideal gas and a non-ideal gas. And so, you know, I can describe an equation state for gases as being ideal or non-ideal. And so an ideal gas is a substance that behaves in a way that all collisions between the molecules are perfectly elastic and there are no intramolecular interactions between molecules. Meaning they kind of behave independently of one another, and when they do collide, it's perfectly elastic. We don't have to worry about any sort of significant energy transfer between molecules in this state. The book states that ideal gas assumptions are valid for when the temperature, what does it say? Greater than or equal to 0 degrees C. And for pressures, I think it said less than or equal to 1 atmosphere. So gases at moderately high temperature and moderately low pressure. So I'm going to put this in quotes, and I'm going to put low pressure in quotes too. If I'm real honest, rule of thumb for a lot of engineering and practicing is we're probably going to consider the ideal gas assumption valid so long as your pressure is below, I would say, somewhere in the ballpark of 10 to 20 atmosphere. But like I said, it really depends on the nature of the species that you're looking at to really understand whether that assumption is valid or not. So the ideal gas equation. This is a really big, important equation. I'm going to pull out all the stops, all the fanfare, just to kind of emphasize that you shouldn't memorize this, but you should memorize this if you understand what I'm saying. All right, so hopefully that denotes that this equation is important. PV equals nRT, or if we're looking at flows, PV dot equals N dot RT. Once again, it relates the species pressure, temperature, volume, and amount, i.e. moles, together in a single function. And so, using the ideal gas equation, if I know 3 of those 4 variables, I can calculate the 4th. So, some important things to note. P is the absolute pressure of our gas. V is the volume. Come on. Or volumetric flow rate. Of our gas. N is the number of moles or molar flow rate of our gas. T is the absolute temperature. And R is our ideal gas constant, where R's value changes depending on the units provided for it. For example, R equals 8.314 joules per mole Kelvin. It also equals 10.73 psia, cubic feet, per pound mole degree Rankine. And it also equals 0.08205 liter atmosphere per mole Kelvin. So the value of R largely depends on the units that you need. So any questions over the ideal gas equation? So let's look at an example. So if I have 150 grams of nitrogen stored in a container at 20 degrees C and 2.1 atmospheres, what is the volume of the container? Well, I have my same ideal gas equation, PV equals nRT. My pressure is provided, 2.1 atmospheres. My temperature is 200 C, but that's not the absolute temperature, that's the relative temperature. So I have to convert that to Kelvin, or 20 plus 273, or 293 Kelvin, is 20 degrees Celsius. Now R, I don't quote unquote have, but I'm looking at atmospheres, Kelvin, and if I look at moles, I can solve for my volume in liters using 0.08205 liter atmospheres per mole Kelvin. So I need the number of moles. Well, I have the mass, which is 150 grams. So if I take the mass over the molecular weight, I can get the number of moles, or 150 grams of N2 over 28 grams per mole gives me the number of moles of N2, which should be 5.357 moles of N2. So now I can solve for the volume. PV equals nRT, then V equals nRT over P, which equals 5.357 moles N2. R is 0.08205 liter atmospheres per mole Kelvin. T is 293 Kelvin, and P is 2.1 atmospheres. And I also do recommend when you're looking at ideal gas equations to check your units, because R only works if the units are right. So atmospheres go away, moles go away, and Kelvin goes away. All I'm left with is liters. So that tells me I've specified everything properly. So if I do that calculation, I have, let's see, 5.357 times 0.08205 times 293 divided by 2.1. So I get about 61.3 liters. Any questions on that? All right, well, I think that's probably a good stopping point for us today. We'll see if we can keep working through ideal gas and non-ideal gas, compressibility, and those things tomorrow. Your next homework 4, is due tomorrow evening. You do have a quiz due on Wednesday at midnight, and then the midterm is Thursday from 11 to 3. So make sure you're ready for that. I'll send out an email later today kind of going over what you need to know for that midterm. It will focus on chapter 4. So don't panic too much in terms of this chapter 5 stuff. I'm not going to put it on there. It's really going to be a focus on chapter 4. Any last minute questions? No? All right. Well, take care, guys. Thanks for sticking with me and have a great day.
Have a great day.